Hi, we're going to continue in chapter 3.6 and pick up in 3.7 a little bit later in today's videos. And in chapter 3.6, we're discussing periodic trends. What a periodic trend is, it is a trend in the behavior of an element based upon the position of the element in the periodic table. And what we use the periodic table as a tool to help us with information regarding trends in the positions either from left to right across a period or sometimes top to bottom down a group. It's a really powerful way that we can visualize the periodic table to help us make some predictions about a series of elements that are given to us, and we learn more about their properties. One particular aspect we discussed during our last lecture was effective nuclear charge. I decided to discuss the effective nuclear charge first because it is important to understand trends in effective nuclear charge if we want to understand other properties of elements that we'll be discussing, such as today with atomic radius. Now, when we think of what an effective nuclear charge is, simply effective nuclear charge can be described as the attraction of our negatively charged electrons, which, as you recall, are situated away from our nucleus, and the attraction of these electrons to that positively charged nucleus. And what we found out during our last lecture as a review, effective nuclear charge does show a periodic trend. Effective nuclear charge increases from left to right across a period. And the reason why that we stated is that we're increasing the number of protons within the nucleus. There's a greater effect of attraction for the added electrons that we get with those additional protons, because those electrons are in valence shells. Core electrons are the electrons that are involved in shielding, and why we get a reduction in nuclear charge. And the effective nuclear charge is this field that these electrons get from that nucleus. So from left to right across a period, there is an increase in effective nuclear charge. How about top to bottom? We have the periodic table here. What do you think would happen if we look at effective nuclear charge from the top of a group down to the bottom of a group? So understanding the effective nuclear charge for a group effect from top to bottom, not quite as intuitive. We're going to think of three atoms: lithium, sodium, and potassium, to help us understand a little bit about effective nuclear charge going down a group from top to bottom. Now, as we said in our last lecture, an important aspect of effective nuclear charge is shielding. Shielding is the blocking of that positive charge within the nucleus caused by the core electrons, and how our valence electrons have a reduction in that positive charge due to that blocking effect. So let's look at lithium. Now, lithium has 3 protons in its nucleus, and it has 3 electrons. It would have 2 electrons in this shell, and it has a single electron in an outer shell. So that's lithium. Let's look at sodium. Sodium has 11 electrons. It has 11 protons. It has an 11 positive charge in its nucleus due to those 11 protons. And it has 11 electrons, 2 in the first shell, or the first principal energy level. It would have 8 in a second shell, the second principal energy level. And it has a single electron in its outer third principal energy level. Real simple model. This is related to the Bohr model. We do have more advanced models. Potassium, remember we're going down this group. Potassium has 19 protons and 19 electrons. So we put a 19 positive charge. That's related to the number of protons. It has 2 electrons in the first energy level, the first shell, 8 electrons in the second, 8 electrons in the third, and it has 1 electron in the fourth principal energy level. Okay, now notice we're increasing the number of protons, so we're getting a lot more positive charge associated with these increasing number of protons. And what's happening, though, is we're getting an addition of electrons, but we're adding electrons to a core level that's sort of spread out. And what we find out and what we get experimentally is this spreading of our core electrons in bigger shells. They're not quite as effective at shielding as we get for going across a period. And what we end up with from top to bottom down a group, we get a gradual increase in effective nuclear charge going from top to bottom. So from top to bottom down a group, we actually have experimental evidence that there is a gradual increase in effective nuclear charge. And the reason for this is that core electrons are less effective at shielding. And we do get an increase in effective nuclear charge as we go down a group, such as we see for this series of elements going down group 1A. And remember, we're looking at periodic trends in main group elements. We're going to keep this model up here for a little bit because now we're going to turn to another periodic trend that's related to effective nuclear charge, and that's atomic radius. So I'm going to move this over a little bit, if I can, maybe not. I'm going to erase this. We'll come back to this model in a few minutes. Maybe I'll just leave it up. And let's discuss got rid of that. Let's discuss atomic radius. And that's a second periodic trend we're going to look at. I'm going to leave this up right here. Atomic radius. And we're going to look at the periodic trend in atomic radius. Let's first of all think about what atomic radius is. What do we mean when we're looking at the radius of an atom? What are we essentially focused on? When we think about the radius of an atom, remember an atom has a positively charged nucleus that has protons in it, and that's that positive charge I show there. And what we're looking at is the dispersion of electron density away from the nucleus. How far do electrons move from the nucleus? And we can think of it spherically. And we get a spreading of electron density away from the nucleus. And that's how we measure, or we can interpret, the atomic radius for an atom. It's based upon how far away electrons move away from the nucleus. Now, experimentally, you might ask, how can we measure a single atom? Do we have that sophistication of measurement? What we do experimentally is we take like 2 atoms that are the same, like hydrogen in its molecular form, 2 hydrogen atoms that are bound to each other covalently. And we'll learn about covalent bond formation. And if this is the nucleus and we have another nucleus here, and they're touching like that, we can measure the distance between the two nuclei. Half the distance between those two nuclei, that's going to be the radius of the atom if these two atoms are the same. So 1/2 the distance between these two nuclei. That equals our atomic radius. So that's how we experimentally determine it. We're not going to ask any kind of questions about it on an exam. I just wanted you to know where it's coming from. Now, the periodic trends that we see in atomic radius depend upon two factors. So let's think about our periodic trends and what two factors influence the periodic trends that we see in atomic radius. Well, depending upon if we're looking from left to right across a period or top to bottom down a group, we have two effects that we want to consider. Let's consider left to right across a period. So if we go from left to right across a period, let's look at period 2 elements. Remember, we talked about period 2 elements. Period 2 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So those are our elements going across period 2. If we move from left to right across period 2, remember our trends in effective nuclear charge? Effective nuclear charge is increasing as we go from left to right across a period. So what's happening as we move from left to right across a period, since the effective nuclear charge is increasing, we're actually pulling electron density in closer to the nucleus, and that dictates the trend that we recognize experimentally. Left to right across a period, there's going to be a decrease in atomic radius. And this decrease in atomic radius is due to the fact that the effective nuclear charge is increasing from left to right. So that's the major effect in our periodic trend in atomic radius. There's an increase in effective nuclear charge, resulting in a decrease in atomic radius because we're pulling electron density in closer to the nucleus. So there's an increase in effective nuclear charge. And that's the major reason there. So left to right across a period, atomic radius is going to decrease. Real important. Let's think about top to bottom down a group. Now, and we're going to use our image that we worked on a few minutes ago right here. We're going to look at group 1A. And I kept this image up here just so we can recognize what do we expect to happen from top to bottom down a group. Well, what's happening from top to bottom down a group? Hopefully these images that I drew a few minutes ago will make sense. As we go from top to bottom down a group, we're actually placing valence electrons in a greater principal energy level, in another shell. And what we get is we get an increase in atomic radius going from top to bottom down a group, because what we're doing is we're adding valence electrons to a larger principal energy level or to a larger shell. So down a group from top to bottom, we see an increase in atomic radius. Now, I saw one person discuss this before, and they used the snowman effect. So this might help you if you're visualizing things. The snowman. Remember snowman you made when you were a kid? The bottom was a big pile of snow, looked like a circle like that, like a sphere. And then we had a middle one that was a little smaller to make up the guy's body. And then his head was on top, which was smaller. So notice that does look sort of like a snowman. Another way to think about it, I have a visual help. Now these, I'll be bringing these out a little bit later. So this is the way to think about our group 1A elements as we go down group 1A. So here would be lithium. It has the smallest radius. Sodium sits out a little bigger, remember? And then potassium has that greater amount of ability of electrons to move away from the nucleus because they're in a higher principal energy level. So that's the major reason going from top to bottom down a group is that valence electrons are placed in greater principal energy levels. They're occupying a new shell, and it allows them to spread out a little further away from the nucleus. So let's use the periodic table and answer a question real similar to what I might ask on an exam. So I'm going to bring up my periodic table. And let's answer an exam type question. I have this example on today's PowerPoint. What we're going to do is we're going to use the periodic table alone, and then we're going to verify our findings with some actual experimental results. But I want you to be able to use the periodic table itself to help make predictions using periodic trends. And we're going to look at atomic radius. So let's list a few elements. We're going to look at oxygen. Oxygen, nitrogen, and phosphorus. We're going to take those three elements and we're going to look at the periodic table here in a few minutes. And what we want to do is we want to rank them. We want to rank them in order of increasing atomic radius. So we're going to rank these three increasing. So it's important to read these questions. In other words, we're going to list the element that has the smallest radius first, the next highest second, and then the largest one last. Everybody good? So let's think of how we're gonna accomplish this. We're given three elements: oxygen, nitrogen, and phosphorus, and we're going to look at them in pairs. We're going to look at how two of them are compared, and then we're going to be able to make our decision from there. And we're going to use periodic trends. Now, when I'm given these three elements, oxygen, nitrogen, and phosphorus, the way I would think about it is let's look at nitrogen and phosphorus in the first, or nitrogen and oxygen. Let's do that. Nitrogen and oxygen. Notice they both sit in period 2, nitrogen, with oxygen sitting to the right of it. So we can make a decision about how we would expect their atomic radius to be when we compare the two. Now, we're going to use our left to right rule. We would expect nitrogen, since it's sitting to the left of oxygen, to be larger in terms of its atomic radius. So nitrogen is larger than oxygen. So far, so good. Everybody see nitrogen is larger than oxygen. Let's look at who else is in this group. Well, we have phosphorus. Let's think about nitrogen and phosphorus now. Now, when we look at nitrogen and phosphorus, we should recognize they're both in the same group. And we're going to use our top to bottom rule. phosphorus is below nitrogen, both of them in group 5A, we're expecting phosphorus to have a larger radius than nitrogen using our top to bottom rule. So phosphorus is larger than nitrogen. So let's rank these three atoms in order of increasing atomic radius. I would expect oxygen to be the smallest, nitrogen to be the next largest, and phosphorus to be the largest of those three elements when we rank them in order using the periodic table. And I have some data on today's, and again, we want to rank them based upon using periodic trends, but here's some data to verify our findings. Oxygen has a radius 73 picometers. Nitrogen is 75. And phosphorus, a whopping 110 picometers. Picometer is 10 to the negative 12th meters. And our expected from our trends meets our experimentally determined atomic radii. So that's the end of chapter 3.6. Our next video, part 2, will involve topics in chapter 3.7. Thank you.